Hi friends, we are going into the 6th class of module 4, and in this class we are going to discuss about what is complete block diagram representation of load frequency control of an isolated power system, which means a single area case. Okay, we have already studied the three block diagrams representing the speed governor model, turbine model and generator load model. Combining these three models, we will be obtaining the total complete block diagram representation of the load frequency controller or LFC. Okay, LFC, load frequency control. So combining these three models, we are obtaining the total block diagram, and here you can see this much contributes to the speed governor model. It's contributed by the speed governor model. This much is contributed by the turbine model, and the third one, that is this much, is being contributed by the generator load model. You can see these are the three transfer functions we have already modeled in the previous classes. So combining these three, we will be obtaining the total block diagram of the system. And one more thing you have to notice, you can see that delta f of s is the output to the system, and there are two inputs to the system, that is delta PC of s and delta PD of s. Okay, so delta f of s means the change in frequency. Because of the two inputs, one is delta PC of s and delta PD of s. What is delta PC of s? Due to the change in the speed changer, normally there is a change in the output power of the turbine. So that is represented as commanded power delta PC of s, incremental commanded power delta PC of s. What is delta PD of s? There is an increment in the load demand, then we will be representing it as delta PD of s. So we are going to make a steady state analysis of this complete block diagram, and this is actually done by taking each of the input independently. For example, in the first case, we will be taking this input as 0, and we will analyze only using this delta PD of s, that is only the change in the load demand. And in the second case, we will be making this one as 0, and we will be only considering this as the input. So that is going to be done, and we are going into the steady state analysis. So there are two important incremental inputs, as I already mentioned, that is delta PC, that is the change in the speed changer, then minus delta PD, that is the change in the load demand. Why it is mentioned as minus delta PD? You can see in this block diagram that PD of s is actually a negative input, and here it is added to the system, that is input delta PC of s is added to the system. Okay, so we are going into the first case, that is, first we are considering delta PC of s as equal to 0, and only change in load demand is considered. So that we are going to consider, in which the speed changer setting is fixed, that is delta PC equal to 0, and the load demand is only changing. And such a system is called the free governor system, okay, or free governor operation. For such an operation, we are going to find out what is the output value, that is delta f of s. We are going to analyze what will be delta f of s. We will be finding what is delta f of s for the case PC of s equal to 0, and only this input is given. Okay, so using a block diagram, we have already studied how to represent the transfer function. Okay, so transfer function, we already know what is the equation for transfer function. Transfer function is g of s is equal to, transfer function is equal to g of s divided by 1 plus g of s into h of s, where g of s is the gain and h of s is the feedback gain. So, where in this case, how can we consider? We are taking delta PC of s equal to 0. So, there is no such an input to the system. Only input to the system is delta PD of s, and the output is delta f of s. So, what is delta f of s divided by delta PD of s? That will be the transfer function. So, from this figure itself, you can find out what is g of s and h of s. This becomes g of s, and this much term becomes h of s. So, this is h of s, that is the feedback, and this becomes g of s. So, let us represent g of s and h of s like this: kps divided by 1 plus tps into s, and second one is h of s. You can represent this whole thing as h of s. Okay. Now, what about the input to the system, that is delta PD of s? This delta PD of s is the sudden change in the load demand. Sudden change in the load demand normally represented as sudden changes are normally represented as a step function. So, the value is delta PD divided by s. Okay, now combining these three ideas, we are going into the actual transfer function, and from that we are going to find out what is the output. So delta f of s, for the condition when delta pc of s equal to 0, your value becomes, substitute all these values in the transfer function, you will be obtaining this complete equation. Okay, and the input is delta pd divided by s. So multiplied by input, you will be getting the output delta f of s. This is the input. Okay, and minus sign is because delta pd is already minus sign. Okay, now we are going into to find the steady state error of the system. So how can we find the steady state error? Steady state error means what is the value at the infinite time t tends to infinity, which means s tends to 0, s into delta f of s. So s into delta f of s, we are substituting this one. So multiplying this one with s, what will happen? This s and s will be cancelled, and in the remaining terms you can substitute s tends to 0. So we will be obtaining delta f of s. So delta f of s will be equal to, delta f will be equal to s into delta f of s. We will be substituting the value and we can find the steady state error as the equation number 2. Okay. Now we can just note some things which we have already studied in the previous classes, that the gain kT, that is the turbine gain kT, it is actually a fixed value. Similarly, in generator load model, we have studied that kps value, that is also a constant value, a fixed value. And the only thing which can be changed, easily changed, is KSG, that is the speed governor gain. So the speed governor gain can be adjusted by adjusting the various links, changing the length of the various links. So this can be adjusted such that KSG into KT is approximately equal to 1, which means this KSG into KT value is approximately equal to 1, so that we have to make such a value, we have to adjust the speed governor gain. Okay, and if this is done, that is equation number 3, and if this is done, then our equation becomes like this. So let us go through what is B and 1 by R. We already know that, or we have already studied in the generator load model, that KPS is 1 by B. Okay, KPS is 1 by B. What is B actually? B is dou PD by dou F divided by PR. What is B actually? B is a per unit value, and I already mentioned in the last class that per unit value is because dou PD by PR becomes the per unit megawatt value, and unit change in the frequency is dou F. So that is why we are representing it as per unit, B as per unit value. Okay, now delta F, now it can be represented as minus 1 by B into 1 by divided by 1 plus 1 into 1 by B divided by R. You just substitute it and you can find the equation for delta F like this. So this is the equation 4, which is one of the important equation, and this shows the change in frequency when there is a change in, only change in the load demand. There is no change in the commanded power or speed changer. Okay, and if this steady changes in the frequency is caused only by the steady state changes in the frequency is only caused by the load demand and not by the commanded power. So one more assumption can be made. This B value is very much small than 1 by R. So we can neglect the value of B, and the equation 4 can be modified as delta F is equal to minus R into delta PD. So you can see this one is actually showing a straight line equation where minus R is the slope. Okay, or a drooping characteristics can be found between delta F and delta PD. So that is mentioned in the next figure, that is a relation showing, or the graph showing delta F and delta PD. This is delta PD and the x-axis in the x-axis and delta F in the y-axis. So you can see it is a drooping cara, and the slope is minus 1 divided by B plus 1 by R, or it is approximately equal to minus R. This is according to the equation 4 and this one is according to the equation 5. Okay, and two characteristics are shown. One is 100% load and the other one is at 60% load. So which means that if there is a change in load, what happens to the frequency? What is the change in the frequency occurring? Okay, now we are going into the second case. Second case is when delta PD is made 0, whereas delta PC is only there. So it is also taken as a sudden change. So the input becomes delta PC divided by S. So what will be the new transfer function, or what will be delta F? What we have done till here, the same thing we are again repeating with the second case. Okay, so let's go into the block diagram and see what will be the transfer function. So what will be the transfer function? You can see delta F of S is the output, and here we are going to consider delta PC of S is the only input, and delta PD is made equal to 0. So which means what becomes the gain? This much becomes the gain for the system, and this becomes the feedback loop. So this one is H of S now, and this one is G of S now. So the transfer function now becomes, you can see this is the gain, and this one is H of S, and the input is delta PC divided by S. So your transfer function becomes delta F of S divided by delta PC of S by S equal to this much. Just substitute and find out. You can see that the equation will be like this, from which you can write delta F of S is equal to this much, or as equation 6. Okay, now we are again going to find the steady state error. So steady state error can be found as S into delta F of S. One more thing I forgot to mention, when S tends to 0. Okay, substituting this equation, when we are multiplying with S, what happens? This S and this S gets cancelled. For the remaining terms, you can substitute S is equal to 0, S tends to 0. So you will be obtaining the equation as 7. Okay, now again, if KSG into KT approximately if it is equal to 1, then you will be obtaining delta F like this. Okay, so this equation number 9 and this equation number 4 are almost the same. The only difference is, in this one you will be obtaining a minus sign, and in this one you will be obtaining a plus sign, and the fourth equation is actually due to the change in the load, whereas here it is due to the change in the commanded power. So now combining these two effects together, what is the total change in the delta F, or what is the change in the steady state frequency? We can find it using the superposition by combining the two equations 4 and 9. So combining the two equations, you will be obtaining the equation 1 divided by B plus 1 by R into delta PC minus delta PD. Why? Because delta PC, you can see that equation is positive, and for delta PD you can see that the slope is negative. So this becomes the total expression. So this is how the speed changer, the frequency is being controlled using a speed governor system, complete turbine, and the generator, load system, everything. So you can study this portion well. Thank you very much. Study well.